Let me get back to it. So I've got a lesson plan today. So welcome to another exciting microprocessor class. It's time to start. Look at that. What we'll do is I'm going to review my little lesson plan for today first. I got a lesson plan just like a professional. Yeah, it's true. So what we've done, and this is kind of a bit of a bummer. I've decided not to hold an in-person lab this week. This is supposed to be our last lab. I was planning on doing something with Ethernet. The COVID infections have kicked up, and I've got to deal with some medical issues that caused me to take a trip to the hospital. So as a result, after due deliberations, I've decided to do our last lab in a remote fashion and make that our final project. And so this will be the last lab. It will be an at-home lab, and I'm going to run a few dates by you so that you can know what's going on. So let's see. I'll do the dates first. So homework 11 will be due the week after the Thanksgiving break. That'll be 12/3/20. That's a Thursday, and that'll give you basically 2 weeks to do homework 11. The final lab will be due on the 9th. That's the last day of that's the last Wednesday of the semester. Hello? Yeah. So late final projects are not going to be permitted, so please do hand that in on time. Last day of class is going to be the 10th, which is a Friday, I think. And then you're going to have a final, which we'll go over due on the 17th, and I'm not going to allow late finals because we have to deal with grading and such. So that's a mashup of all the previous homeworks done using Blackboard and remote learning, 2 attempts, and I haven't made it up yet, so I can't answer too many questions about it because I really don't know. So I summarize these as part of these dates as part of the instructions in homework 11, just so that you could have them on file in case you don't have a chance to write this down. You'll be able to refer back to these dates. But eventually you should write them down. You should write them down in your calendar because they're important, things like finals and final projects. And what I wanted to do today was go over the final project, go over the homework 10, which is due on Thursday the 19th, and start to go over and maybe finish going over homework 11, which will be due the Thursday of our second to last week, the week we come back from our Thanksgiving break. Well, virtually come back because we're not physically coming back, right? So let's think in terms of strategically about our final project. This is going to be essentially the last assignment for our lab, and it's going to count for 3 labs. That's the way I'm running on this because we didn't really have a midterm, so we'll just make this count, like, because it's being done over a 3-week period. We'll make it count for 3 labs. I don't think it's 3 times harder than anything else, but it's a project and you do it on your own. You've got your Arduino Uno. You've got your audio shield. You'll need both of these things in order to do that lab. And what you're going to do is you're going to build a telephone touch tone synthesizer. And I'm going to describe for you in a minute what that's about. It's, I don't know. Let's jump into the Wayback Machine here. 1963. And AT&T has decided to go from a rotary telephone to a push-button telephone. Now, some of you all are youngins, and you'd never seen a rotary dial phone.
Funny enough, I've actually used one before.
You have used one? Yeah, I've
Yeah,
got.
when I was young, my neighbors had one.
Well, I've got several. And you're no longer young. So there. So this is a rotary dial phone. That's a desk model 500. And that represents a couple or 3 decades worth of phone. I mean, that's been around for a really long time. This is a candlestick phone. The typical rotary dial phones came in colors, although initially they were black. It is the case that you can still buy them, at least, well, if you want to buy a used and terribly old phone. And under certain circumstances, yes, they will even work. In fact, you can get a dial to touch tone transcription. Oh, geez, we could do this with an Arduino. A dial to touch tone converter, which will allow you to take your touch tone phones and use them on regular, take your rotary dial phones and use them on regular touch tone lines in case your touch tone lines don't work. In fact, a lot of times what happens is you call up a voice tree, and the voice tree will say, for English, press 1. And if you're on one of these things, good luck, because you're not pressing 1. That just doesn't work. And so this is a way in which to do control of what's known as a circuit switched system. Circuit switch systems are that's a whole other discussion. They're the mechanisms by which operators used to take switchboards and route your call from one central office to another and finally to another station. During that routing period, you would wait for the call to be connected, and then once it was connected, the other station would ring. Didn't used to be that people had rotary dials. They would just have cranks. These were called crank phones. I don't know if you've crank phones. I don't know if that's why people call them cranks, but well, crank phone. A crank phone. It's got to be in here somewhere. There it is. That's a crank phone. See, it doesn't have a dial. On the side, you have a thing that you turn that's a generator. Generates 90 volts, and it energizes a ringer at the central office. You remove the carbon earphone, and you talk into the carbon microphone. It rings at the other station in the central office, and then you get an operator that answers the phone by plugging in a jack into her switchboard, and then she says, number, please. And then you say, well, I want, Murray Hill, which is the name of the central office, and then 467, which would be the name of the station. And then she might say, as part of her protocol, just a minute. And then she would route you to this other central office and then proceed to tell them that you wanted the 467 number. They'd connect you up, use the central office 90-volt generator to cause their ringer to ring, and then you could have a conversation and you'd have a guaranteed quality of service. These types of phones were around for a very long time until people decided they wanted to automate the operators out of existence. Toward that end, they created the rotary dial system. And the rotary dial system essentially automated the switchboard out of existence. So, there were switchboards up until the 80s, actually, but it took a long time. Switchboards. I think there was one in Maine. It was the last one, if memory serves. Switchboard in Maine, and I think there's a picture. And yeah, there they are, sitting there waiting for phone calls to come in. And you can actually find one of these switchboards if you go to the radio telephone vintage communications museum up in Windsor Locks. They have these things there. You can play with them. It's great fun. And then they also have an automated stepper relay system, which allows you to automate the operator out of existence by using the rotary dial. So if you are looking at a circuit switch network, this would be a this is a real hard network. This is a circuit switch network, because the switching is done in the circuit in the patch bay, and then the actual and you could see patch cords sort of hanging down here. They made them like furniture. Aren't they pretty? I mean, this is like a piece of woodwork right in there. Somebody actually, like, I don't know, finished it and sanded it and just made it nice and everything. So that's a characteristic of a lot of the electronics from that era. It's all made out of wood. They weren't making things out of metal, and Bakelite was the only plastic that was available, and it wasn't particularly robust. It was very fragile and it would crack. So as a result, if you went to automation, you got what was called a stepper motor, a stepper relay. Stepper relay switchboards. Right, this is a history lesson. Stepper relay switchboards were basically like this. That's a stepper relay. And they would be ganged together in gangs of 7 or more. And then each time you dialed one number, the stepper relay would go to another position. And that essentially is a circuit switch network, but the switching is automated or semi-automated. Actually, you become the operator because you operate these switches remotely by using the dial. And so your rotary dial corresponded to the rotary positions on this switch, which is kind of cool. And here's a bank of them, and they're installed in a telephone system. So there's a bank of rotary switches, and you can use these to dial out. And you can see them dialing out from a handset. If you go to the museum, you can see them running in real time as they tick along one digit after the other. So they decided to turn all of this electronic using the push button system based in what's called the dual tone multiple frequency in-band plain old telephone service, or POTS as they call it. So in the voice band, what you get is the ability to dial by pushing buttons, and the buttons generate these different frequencies, and they're A through D, 0 through 9, star, and pound, and they're arranged in this fashion. And what you have is frequencies on the horizontal part, and other frequencies which are on the let's see, horizontal part, and other frequencies which are on the vertical part, and they're arranged in the following fashion. So here you can see, this is why they call it dual tone multiple frequencies. If you want a 1, you press 1209 hertz and 697 hertz at the same time, and that will create a 1, which is audible. And so it goes into the line which is capable of handling voice. So these are not just audible frequencies, but they're in the voice band of the plain old telephone service.
Does it, so those tones are the tones that the button makes when you press them?
Yep. That's
Okay.
exactly right. That's exactly what they do. So
And do they add those two frequencies?
yeah. So you add a 1209 sine wave to a 697 hertz sine wave, and you get a 1. That's exactly what it does. That's exactly what it does. And so what I did was I wrote a program in Java. And what I did, I'll do the demo first. Let's see if we can get this to work. Is, see, you can put in a phone number, 203-555-1212. And let's see if this works here. And those are touch tones, and you can actually enter in characters, and they will map to the numbers of on the keypad. So if you said, just dial 1-800 MATTRES, leave off the last S for savings. I don't know why I remember this. Maybe because I've watched too much television or something. it'll translate it. So I don't know if that was enough numbers or not, but it was supposed to be close. So that's the that's that. And so what you're doing here is taking the string and mapping it into a series of tones, which then get played through the speaker. The interesting part is the part where you get the tones. And so what happens in here is each one of the Dtmf characters maps to a set of frequencies. So when somebody says here, let's dial in A, these are the two frequencies that come through. B, I think we can say safely, here's case number 1, 1209 to 697. And now if we go back to our homework assignment, our little final project, we should see.
Wait, how long is your code? 300 lines?
Yeah. So then here it is, 1209 to 607. So that's a set of frequencies. Let's do another one. If I want to dial a 5, it's 1336 and 77 hertz. If I go back to 5, we should see, yeah, 1336 and 770 hertz. So the case statement basically dispatches on the characters or letters that are underneath those numbers, right? And then tells you what the frequencies should be for the dual frequencies. And so this in-band mechanism of communication has been with us for a very long time and is used to control what we call in-band control of the voice tree, right? So somebody says, for Deutsch, presse 9, and so you have to press 9 if you want German or something, and so that's that's a typical sort of thing. And they'll go through all the languages because there's only 450 of them or something.
I have
So
a question.
yes.
Could you, instead of doing a case for each letter, could you do like using like an ASCII code and just doing the numbers from this letter through this letter, like give me this tone kind of thing? Because I know like on a telephone there's like three letters on one button, right?
Yeah, I mean that's right. So if you look up, I've got a telephone here next to me. I've got a 9 key, and next to the 9 key it says WXYZ, but next to the 8 key, it only says TUV, and next to the 7 key, there's actually 4 letters. It says 7 is PQR and S, and so it's not always the same number of letters, and the letters aren't necessarily related to the number 6 in any sense when you go M and O. So the reason I listed them like that is it seemed to me like it was the easiest way to do it.
That's fair.
So
Okay.
that was how I arranged it. But you are at liberty to, use it or lose it in terms of my technique. Obviously, there's more than one way to program these things. Oh, and there's more. There's more. So let's take a little guided tour of the code. So now when I make a new instance and I have the 2 frequencies, so the first thing you want to do is you want to take the character string, break it up into individual characters, and then one character at a time determine what the 2 frequencies are for each one of the characters. Once you have that, once you know F1 and F2, you want to make the signal that you plan on using to play the sound. So then you have to figure out what your duration is. I put mine in for 62 milliseconds, but you could make it longer for sure. And then if you wanted to play the frequencies, well, I have this thing called an oscillator, which allows me to get a sine wave given 2 frequencies and a duration. So that's how I chose to do this. Now, when you look at this, you'll see that I have used the trig function and a sine wave, and I've made an oscillator waveform that ranges from -1 to +1 and is using floating point numbers and is totally unsuitable for the Arduino, but is okay for, a desktop computer where you're just doing something, to be educational. And so when you look at this, You see totally impractical code. It's returning double precision numbers. It's taking the sine waves and directly invoking trigonometric functions, which are heavy duty for an Arduino and not suitable. And then it stores them it stores the waveform that it synthesizes, and then proceeds to return that waveform. So this is a fairly heavy handed way to do the programming, and is not the way you would do it for um, an 8-bit toaster controller like the Arduino. So take this idea, very interesting idea, very nice, thank you, throw it away, and then start again. Only this time we create, ta-da, the DTMF generator for Arduino code, which actually is inspired by the Java code, but is now meant for 8-bit toaster controllers that don't have things like real-time or very fast generation of sine waves and cosine waves and things like that. And so now we've got sort of the same thing in a big way, with a difference. And the difference is we've got a little library. And the library is supplied to us by somebody who decided to use an R2 resistor ladder. And so what they did was they went through and created the sine wave in a wave table, which is really nice because now you don't have to use trig functions. It's just a lookup. And that's kind of the way to go, actually. And then look what they've got. It's a case statement. And the case statement is basically just telling us the frequencies for character 1, character 2, character 3, 4, 5, 6, 7, 8, 9, star, 0, hash. But they didn't do, the other ones like A, B, C, D, which you could do. And certainly you can add those in because you know what those frequencies are now. So you'll have to make a little bit of a modification to add those in. And then what he does in order to be able to create the output signal is he writes to the DTMF port. That port is actually just port D on the Arduino. And what he's doing here is he's adding two integer numbers off of the wavetable, and then he assigns them to the port so the outputs are asserted as either ones or zeros. And when he does that, it goes through his little R2 ladder and makes a little signal for him. And that works reasonably well. And that's a good idea. I mean, you can do that and that's fine, but we don't need to do that because we have a 12-bit MCP 4921 DAC, right? That's on our audio shield. So our code will have to be just a little bit different. So what I did was I said, look, instead of writing out to that line that he's showing you, I'm giving you hint, right? Here's the hint. You may like to use an 8-bit DAC method in your code, something along the lines of DAC init. You're going to have to init your DAC. You'll have to include your SPI interface. And then there's this thing called DAC write, which takes a byte and then transfers it over to your DAC. So if you put that into your code, if you choose to use this code, and you may like to, you might want to put it here under dtmf.cpp. And then you probably have to modify your .h file to include an invocation to it, because you're going to want to start to write out those values to the DAC instead of simply setting the data direction register. In fact, you do not want to set the data direction registers, nor do you want to set the output register value, because if you do, it might mess up your MOSI MISO stuff or your SPI interface. So, setting the port like this, that's not good for you if you're using an SPI DAC. So you're going to have to modify this code somewhat, but that's all right. Now, this code has been disseminated in a library, And if you manage the libraries and you do a little search for DTMF, you should be able to find it. So what I do is I just click on this little text field over in here and I type in DTMF and I hit enter, and sure enough, here's the DTMF generator. And if I hit more info, you'll see the original code. And if you want to look for the layout, here's what he did. So you can kind of see, yes, I can make an R2 resistance ladder and I can make a DAC and that'll work. But you guys have the audio shield and it does the SPI interface. So you don't have to build this. You shouldn't build this. You should do like use the audio shield. I think that's a much nicer way to go. And besides, this is only an 8-bit DAC and it uses all the ports. All the ports. So with an SPI, you're only using like 4 wires or something. And you get 12 bits. So a couple things going on here. First of all, he's laid out his library so that his C++ and header file are separated from his examples, right? And what I did was I included a zip file, and that will enable you to obtain the code dtmf generate.zip, so that when you open the INO file, it'll become nicely laid out for you, and it will look just like this. So that'll make it nice, and then you'll be able to go in and swoop in and change the output port so it uses the SPI DAC, and that's the deal. That's the project, really. And if we read it, we can see, there are a couple of things in here like details. You can drive very light loads with the DAC, but in general, you need amplified speakers. Any speakers of any substantial size, you can't drive them directly. If you want, you can use like little iPad earphones or iPod earphones. They'll work okay. If you have amplified speakers built into the computer monitor, that'll work okay. If you have computer speakers, that'll work all right. This is the data sheet from Microchip, so that's just a convenient thing. There's the 8-pin SOIC, small outline integrated circuit, which is built into the audio shield that you're using. That's a nice, elegant way. Sometimes I think, well, gee, if I didn't want this, what could I do? I could get a shift register, and then I could get an R2 ladder, and then I could essentially build this chip. But then I said, well, why would I want to do that when this chip is so inexpensive and he's already got a shift register and his own R2 ladder all built into the integrated circuit? So that's why people, sell these things. It's worth it. It takes up a lot less space, works better, yada, yada, yada. So plus you can get it in stereo if you want. I mean, it's a nicer way to go. So that's why people use these sorts of chips. They're not terribly expensive. And it runs fast. I mean, it's at 20 megahertz clock support, faster than our Arduino will run. So that's cool. And so then let's see, what else do we need to know about this lab? Let's see. I'm just going to read it, make sure. This is your final project, counts for 3 labs, but you will have 3 weeks to do it. So basically, I assigned 300 points. So that's what makes it count for 3 labs, so that you can get a maximum of 300 points on this. Let's see now. You're going to use your Uno and your little 12-bit SPI DAC. You're not going to plug it into speakers or that'll blow it out. You're going to use earphones. You got your data sheet. Here's the thing about touch tones. What else do we need to know? Somebody have a question?
Yeah, I was gonna ask about how you're gonna, like, what do you want us to deliver to you from this project exactly?
Okay, so you're gonna have to hold your suspense, because it says here your submission will consist of. So it's a very timely question, actually. a zip file with your code and an audio file in MP3, AU, or WAV format, or a video file with the audio created by your program. Although you'll be taking a video of your Uno running, which probably won't be very animated. If you cannot get things to run properly, please mention this in your submission so we do not spend a lot of time trying to get things to work. I'm going to try and get your code to work, And then in principle, if you make an attempt and it doesn't work, you get partial credit. But let us know so we don't get aggravated trying to debug it. And then here's the Dtmf frequency map. Let's see now. Dtmf resides in the voice band. Here are the symbols. We do not normally use ABCD in our keypad, but the standard does permit them. Someone has already done this with the R2 ladder. You could see that. But you're going to use the MCP 4921 DAC. And when you're done, your software should be able to play the sample code in the zip file attached to this assignment. You'll have to modify the code to play the frequencies A, B, C, and D, and to make use of the DAC in your audio shield. You may here's the hint, you may like to use the 8-bit DAC method here, which allows me to output to the DAC, and that might help you out a bit. And here's the frequencies for A, B, C, and D in case you don't have them handy. And let me see if there's, okay. I think I got the answer to your question in this one paragraph, which is your submission will consist of. Does that answer your question?
I still have another, so you want, so how are we going to input into this Arduino setup, and how are you going to hear the audio is my question.
Okay, so you're going to submit a zip file with audio, and I'll be able to hear the audio in that zip file as well as look at your code. So that's how I'll hear it. And then your question is, how will I get my Arduino to play the audio? And the answer is you're going to use a modified version of this code, and that's going to play the audio. So that'll generate the output.
So I'm going to put like a series of numbers as an input to make a noise, right?
Right. So let's assume that you wanted to, I mean, here we are playing a key, and the key starts with a character 0, right? So now let's assume that you wanted to play 0 through 9. Suppose if the key was greater than 9, you could start it off by saying, okay, let's play keys. I don't know, make up A through B. That would be all right, I suppose. Then for char letter equals, quote A, while letter is less than, quote, E, letter plus plus. So that sort of works. And then Dtmf generate. So that's a reasonable thing to do, I suppose. As a matter of fact, if I wanted to do it up in this vein, I could probably just use key for this, key for that, key for this, and then looks like we're delaying 1 second between each letter. I'm okay with that, I suppose. Then if you wanted to, yeah, forget about the LED. I don't care about the LED. So now do it again, only with a difference. And the difference is start with 0 and move your way to there.
So you're not. So we're not really putting an analog input into the Arduino.
Oh, no, it's a synthesizer. It's synthesizing analog output.
Okay. What I had in mind was like we were gonna recreate like the actual number pad and have it make noise for each button that is pressed.
No, 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 no. We're not
Okay.
going to put it. We don't have physical buttons. These are just generating the keys that you would normally be able to press. I mean, if you wanted to, we could input a string using the serial port and have, you type it just the way I did for the Java program. But I feel that that is unneeded complexity. This is complicated enough the way it is.
Okay.
Later, if you wanted to scan for buttons and you wanted to play things live, it would certainly be more than possible. It's routine engineering to scan for the buttons. So uh, you have there's no I would say issue with scanning for buttons to see if buttons are being pressed. That's simple, I think, isn't it?
I guess. Okay. I was just confused because I thought you were modeling an actual number pad. All right.
Well, it is kind of a model in a way. If you wanted to take a look at my dial pad, it actually does not, it models the touch tone keypad and allows you to generate audio so that you can proceed to dial using either a serial port or a speaker. And then if you wanted to dial 1-800 MATTRES, leave off the last S for savings, you can do the letter to number conversion, and that will actually be the numbers that you would have had to have typed in order to get those letters to come out. So if you wanted to dial 1-800 DocDorb, the B is for bargain, then dial 1-800 DocDorb, and you'll get the, whoever that is who I think that's the fellow who advertises on The Simpsons. I think he does his surgery with tools from his garage. So, right, if you don't mind a hack using a hacksaw on your body, I suppose dial 1-800-DocDorb and just think of all the money you'll save. So that's a sad commentary on the healthcare system. I crack myself up. So then therein lies the project, such as it is. What do you think? Does that sound like a project? Can you guys figure this out?
I think it'll be fun.
It should be. I mean, I tried to get something that was the right level of complexity for a 3-week project, a final project of the course. Now, here's my proposal to you, the class. If you don't like my project, you have until Thursday to propose an alternative possible project. So therein lies an interesting opportunity, because I thought long and hard about whether or not people would like this project or wouldn't like the project, or maybe they have their own ideas of what they want to spend their time doing. And it's your course, so you need a final project. So if some individual comes to me between now and Thursday and says, "Oh, Professor Lyon, I really want to build a printed circuit board that does X, Y, and Z. And I'll just say yay or nay very quickly on that. I'll turn that around quick so that you can have a chance to get to work on your project over the Thanksgiving holiday. So that's an option. You guys, you can have your own. Just make sure it's not like a clone, right? This project is a lot like a clone of another project that already exists, with the difference, and the difference is very small. The difference is we're going to use the SPI DAC instead of the R2 resistor ladder. Other than that, it's not a particularly remarkable difference, and I thought that was enough of a difference to make that into a project. So if you're going to pick a project, make sure it's not too complicated. It can be built on, the shoulders of somebody else's project, but also, don't make it too simple. So we got to get the right level of complexity here. So that's that. That's the project. Are there any questions? All right, so give it a think. If you don't like this project and you'd rather do something else, I might be okay with that. Just let me know what it is you have in mind, and make sure I approve it before you go off and do it. So, right, so everybody's okay with this. I'm sort of pushing it to the side now, and you'll have an opportunity to ask questions about it again on Thursday. And as far as Wednesday is concerned, in case it wasn't clear, we're not meeting in person on Wednesday. So I'm not going to be there. And this is a do it on your own sort of final project. And I have scoured the web and I have not found anyone who has anything quite like it. So it's not something you're going to find through the Google as far as I know. But, I could be wrong about that. Just to be clear, there are other DTMF libraries. The other DTMF library, and you can sort of look at this. It's kind of interesting. Uses hardware. So he uses an MT8870 DTMF decoder. So the decoder is interesting because that will actually decode these tones in hardware. It's a filter bank, and it's kind of an interesting chip, but it's just a decoder. It's not a synthesizer, so it's going in the wrong direction for us, right? It's doing the same frequencies and all this other good stuff, but it's not what we're doing. So it's a little bit different. And then if you wanted to, you could look at the data sheet on that one. Here, it's a little chip. You can buy these decoders. So in fact, you could plug this into your Arduino directly. I've already ordered one. I don't have one. I should have one. And then it will output to these signaling digital outputs when it hears a tone that it can decode, which is really interesting because that means you could use this device to control a piece of hardware from a telephone that picks up the phone and then proceeds to listen for touch tones, which is, kind of cool if you're running sort of like a ham radio rig and you're trying to get to a repeater. You can control the repeater remotely with this little DTMF decoder. In fact, we could write an Arduino program for that. You don't need their chip, but it's not a particularly expensive chip and probably works really well. I don't have one, so I can't really tell you, but it's integrated DTMF receiver from Zarlink. Who the heck are those guys? Zarlink, the last word in DTMF decoders. Really? I don't know. Zarlink. I've got to look those guys up. This is an exotic chip. I mean, this is like truly a mixed signal kind of chip, kind of clever actually. So that's that. Any other questions about this project? So that's your final project as far as it is concerned. And if we have more questions, we can certainly try and address them. let's have a look at the agenda for today. So on the 19th, end of day, you're going to have a homework 10 due. Are there any questions about homework 10? No questions. All right. So then after the Thanksgiving break, we're going to have a homework 11 due. So here's homework 11. And now, let's see now. We saw the power required for the WizNet board and the power requirements for the other Ethernet shield. And I had made those points because I had thought we were going to do an Ethernet project in the lab this week, but I guess that's not going to happen. And so as a result, it's kind of a non-issue in terms of, having to plug the Ethernet stuff in order to get enough power. I don't recall if we saw the Telnet server. So what I'm going to do is I'm just going to quickly play that. Copy link, new and paste. Oh, that's blurry. So what you see in here is an IP address that's local, non-routable, 192.168.1.177. And then he's creating a socket which he listens to, and that socket is listening on port number 23. So it occupies that port. So the Arduino now becomes a Telnet server. Then I create a buffered ring reader from an input stream, which uses the socket's input stream in order to read the output from the Arduino. I go to the same socket, I get an output stream so I can write to the Arduino, and I put auto flush true because I want to be able to make sure that every time I go out.println, it automatically sends it, doesn't buffer it to the Arduino. I print out ready. Then I do out.println so that the Telnet server sees that there's somebody present. And then I do a br.readline to read until the end of the line. And I expect numbers to be comma delimited. So I split those numbers into an array of string based on their commas. So every time I see a comma, I create a new array element. I parse the two different array elements I'm expecting. And then I proceed to print them out. So I'm using Ethernet and TCP/IP as a substrate to separate me from the hardware. So now I've got a clean, high-speed, network-based interface to a piece of hardware that could be embedded into a system for command and control. And so that's a way in which you can essentially plug in different hardware systems with our Ethernet shields and make networked embedded systems. And that's the point, right? Because now if I want to control motors or measure sensor output or try to do something that involves any type of command and control of an embedded system, like for example, I could type in a command that brings the temperature of the water up to boiling and then holds it there for, I don't know, 10 minutes or so I can make sure that I've essentially boiled the wort in my beer making contrivance. I can use this as an embedded system with a network interface so that I can proceed to create my little beer Duino. Beer Duino makes beer with an Arduino because I don't know what to do with an Arduino, but if it makes beer, I figure that's good. And so Bearduino needs to have some sort of a controller interfacing it. And I like the idea of interfacing Bearduino over the network unless some Russian hacker comes in and, I don't know, tries to hack my beer. That, you know, that's like an act of war or something. So that in and of itself is a reasonable way to go. I've actually built little stepper motor controllers at the end of the Arduino. There's another thing you can do, and this is pretty cool. You can use, let's try this. So now we've got the, see if this works. Didn't we just do this?
I think we saw this last class, right?
Yeah, we just saw this.
Yeah.
Let's go to a different, it's supposed to say mouse control. Open in new tab. Let's see if that works. Now we're getting somewhere. So now we can use a socket to control the mouse on the computer. So this is using the Ethernet with the same IP address. And what he's going to do is he's going to take the X and Y coordinates and actually move the mouse using the Arduino's A to D converter to measure the voltage on the potentiometers. So now you've got, completely different languages running on completely different computers, all running with the substrate of the TCP/IP protocol on the Ethernet, and that enables you to, uh, well, essentially plug in completely disparate hardware and have it used in totally different places. Although well, I find it convenient to have the Ethernet controller right next to me because I'm still experimenting. But at some point, you could say, well, it's sitting down in the plant somewhere, wherever the plant is, doing whatever it's doing. And so that's a way in which you can do embedded control with the Ethernet. So here it is. Here's the shield, such as it is, and it's just one of many that you can get, and we have actually several. This one happens to use the WizNet chip, which implements the TCP/IP stack. And interestingly enough, it also comes with an SD card slot, so you can slap that in there. And if you were in need of logging data to something that you could upload later when you were connected to the network, this could do that. It could store it onto the SD slot. So it just, because this chip takes so little space, they figured they just give you this because why not, I guess. They figured it's a great feature. Frankly, I've never used it, but I'm sure we could if we wanted to. And so what we have here is a hardwired Ethernet controller chip, which lets us plug our Arduino into the Ethernet. And, you can use Wi-Fi for things, but I kind of like the Ethernet. I think that's really nice. And so the answer to that one is true, right? That is a hardwire Ethernet controller chip. And you can look these things up, right? I mean, if real engineers use data sheets, it would be really good for us to be able to use the data sheet on any chip we'd like to, but you can't always do that, right? I mean, that's a bit of a luxury. Let's see if you can get the data sheet, right? Because if you're well, if you're Apple and you make CPUs, but you don't sell CPUs, then the data sheet becomes proprietary, and you can't find the data sheet for the M1 CPU or the A14s or anything. I mean, that's just weird, right? Because every CPU manufacturer wants you to use your CPU, use their CPU in your designs, except for Apple, because I don't know, that's their proprietary thing, I guess. And so this is here's the block diagram. Now you can see what's going on. The WizNet, that's everything inside of the little oval square. Can you have an oval square? It's in the oval. And so it shows you that it has the TCP/IP stack. It can do PPPoE, which is point-to-point protocol over Ethernet. It knows one of the media access control layer protocols, and it has a physical Ethernet interface. That's the key right in there. So you can plug this right into the Ethernet. Let's see what else we can see about this. So there's this thing called the OSI model of networking. Have we had a discussion about that? People, so OSI, that's the open software interconnect model. And that has 7 layers of abstraction, so that you have the physical layer, the data link layer, the network layer, the transport layer. You have the session layer, the presentation layer, and then you have the application layer. So, not to put too fine a point on it, if I had to write this down somewhere, where can I write it? I don't know. I'll write it on my Arduino sketch or something. There. So you need the physical layer. So that's for your bits. Your data link layer. That's for your frames or packets, if you like. In point of fact, the OSI protocol calls this data link protocol units. I hate that name, but there it is. Then you have your routing, which is done in the network layer. Then comes the transport layer. Then comes the session layer. Then comes the presentation layer. Then comes the application layer. And every layer has different roles and different responsibilities. So at the network layer, we would have routing. At the transport layer, we would have flow control. At the in common parlance, this is where you would have Internet Protocol, IP. This is where you would have Transmission Control Protocol or User Datagram Protocol. So you can have TCP/IP, or you can have UDP, User Datagram Protocol, on Internet Protocol. Then comes the session layer, and that's going to be responsible for things like hypertext transfer protocol in security. So this would be the so-called secure sockets layer. Then comes the presentation layer, and that might be a hypertext transfer protocol and or HTML, which then gets rendered over in the presentation layer. And that's where your browser is hanging out. So your browser uses HTTP to grab HTML, but it can use secure sockets layer in order to have that level of security. The error control can happen at every layer. And in fact, it can happen at it doesn't have to happen at every layer, but it often, you could do error correction anywhere or everywhere. And so that's an outline of the OSI protocol. If you wanted to pass instances of objects from one machine to another, then you might use something like Corba, which is the Common Object Resource Broker Administration. That's a object management group, or oh my God, standard, OMG standard. Then there's the RMI, which is Remote Method Invocation. So that's a native object passage mechanism embedded in Java. So that's this is what you'd be using if you were writing in COBOL in Hartford at an insurance company, and you wanted to talk to your Java programs. Java can talk Corba. But if you were writing like for a company that actually programs in Java, you would use RMI to talk to Java because Java natively talks to RMI. The other languages that might support Corba include things like Fortran and stuff like that. So if you were working at Sikorsky and they still have Fortran there, you could call your Java programs from within the Fortran environment. So that's that's the 7 layers of network abstraction in the OSI model of networking. And that's still useful. So then it says here, the physical layer of a network layer and the one that is responsible for transmitting bits from one place to another. What does this mean? Uh-oh. This is not decent English. Just a minute. Wow. Okay. That's unfortunate. Let's go to question 3 and just fix that right now, because that's kind of broken, actually. Sorry about the English there. Question title. I guess we'll call this OSI question. And physical layer and the network layer are the ones that are responsible for transmitting bits from one place to another. And then the answer to that would be false. That's not what their responsibility is. Physical layer is for bits, not the network layer. Oh, it looks like somebody's already taking this test. How can you guys be so fast? I just made this public like this morning. Whoa. Yeah, sorry about that. Change the answer key on you. Don't be too quick on the trigger on these things because I still have to review them. So then here comes the second layer is the data link layer. It is responsible for delivery of frames between devices on the same local area network. That's true. The data link protocols are Ethernet for local area networks, multi-node, and the point-to-point protocol. Also true. So the network layer is responsible for packet forwarding, including routing through intermediate routers. It is the third layer up in the OSI protocol. Examples include IP version 4, IP version 6, and Internet Control Protocol, Internet Control Message Protocol. And that's how routers speak to one another. And that's also true. Let's see. The fourth layer is the transport layer, responsible for connection-oriented data stream support, reliability, and flow control. Examples include TCP and UDP, and that's also true. And we saw that in the, here's flow control. And examples, UDP and TCP. Fifth layer up is the session layer. Session layer provides the mechanism for opening, closing, and managing a session between end-user application processes and remote procedure calls. That's what you would do if you were programming in C or C++ and you were calling one program running on a different process, a different machine from another. And by the way, we can do all this stuff if you want to take communication networks programming, but we don't do it with the hardware, right? We'll do it with software. Whereas in this course, we could do it and, do these sorts of distributed computing applications with the hardware, which I don't know. I kind of like the hardware. That just makes it slick. So that's an opportunity to do authentication, authorization, session restoration, and checkpointing and recovery. Yes, all true. Session layer. Here comes question 8. The sixth layer up on the OSI model is the presentation layer. And you can see that is true right here. And then it says it does serialization. Serialization is when you take an instance of a object and you convert it into an array of bytes. And then take the array of bytes and pass it through an output stream, which you may have gotten from a socket. You can get your output stream from anywhere. You could write it to a file output stream and essentially achieve persistence by saving instances to a file. So if you said, I want to save payroll, but I don't want to have my own file format for payroll, I'll just make an instance of the payroll, write it to an object output stream, which goes to a file output stream, and I will have saved the payroll out to a file, which I could read in later if I wanted to read in payroll. RMI, remote method invocation, it only works because of serialization. So in other words, I can't get the answer or even pass in the question without using some mechanism that's going to take the data and get it to move from one point to another. So that's what serialization is really about. So 6th layer up, presentation layer, the serialization, RMI, HTTP, relieves the application layer of concern regarding syntactic differences in data representation. That's true within the end user system. EBCDIC, I don't know if anybody uses EBCDIC. I think it's extended binary coded decimal interchange something or other. EBDIC. EBCDIC. Yeah, somebody knows about it. EBCDIC wiki. Isn't it extended binary coded decimal interchange? That's it, interchange code. This is what IBM mainframes used to do. They would, there'd be an American standard code for information interchange, and IBM would say, "Fe on you, we're making up our own." And so they had their own means of encoding characters, and they called it EBCDIC. And then anybody who wanted to communicate with these guys and their punch cards, needed to convert from ASCII to EBCDIC and back again. And so that's something you might do in the presentation layer, relieving the application layer from having to do that conversion. This is the Hollerith punch card. In fact, there is a Fortran statement called 1 Hollerith 1, 1H1, and when you use it in your print, it actually ejects a page. I did this once when I had a car. I wrote a program for a high-speed mainframe. It counted to like 1,000. And I was testing the different formatting codes. And 1 Hollerith 1 was when I tested, so it ejected at extraordinarily high speed, 1,000 pages. And the operator told me I was a turkey and told me not to come back. And I basically alienated the operator over at the NYU Courant Mathematical Department. They had a Cyber 76 high-speed mainframe, and I was screwing around. Let that be a lesson to you. 1 Hollerith 1. So then, yeah, I don't know if you guys will ever get around to programming in Fortran, but it's true story. So then, let's see. The 7th layer up is the application layer. Some protocols for this are, and Telnet, file transfer protocol, trivial file transfer protocol. That's actually interesting because you can upload firmware to your router using trivial file transfer protocol, because sometimes routers need updates. And I am always resistant to putting updates into my router, but if your router has an admin interface and wants to check for an update, and I think mine probably needs one. So if I went to 192.168.1.1, I could probably find my Netgear router, and somewhere in here it'll tell you whether or not you can, a new firmware upgrade is available. It said this for like a really long time. And if you want to download the firmware upgrade from Netgear and then upload it, you need trivial FTP, and that'll do the upload. So that's kind of a typical thing people do with routers. It's it's probably a good thing to use for Arduino because it's trivial. And then there's the mail. That's a protocol, mail protocol. Domain name service is a protocol. A lot of protocols. You get your protocols from people who propose them. And what they do is they give you an RFC. RFC for DNS is probably, yep, there it is. So somebody, 1987, came up with this idea that you wanted to be able to resolve IP addresses into domain names. And so they came up with the DNS protocol. They proposed it by putting out a request for comments, and this became the de facto industry standard for DNS. Isn't that cool? So you can basically create your own protocol and propose it, and if the industry likes it, maybe they'll adopt it. I don't know. You guys can join those things. So this is all the time we have for now. We got up to question 9. So keep track of that. And we'll start off from question 9 next time, which will be on Thursday, because we're not meeting Wednesday. And if you have any questions about, what to do for your project and you don't like the project I proposed, let me know. And I'll be able to give you an answer pretty quick. Well, thanks a bunch. Hope you liked my little lecture there, and have a safe day.
Thank you, Professor.
Thank you.